All right, so we just set up our complex plane where we're going to graph complex numbers. What we would normally refer to as the x-axis is where real numbers are, so that's numbered normally. The y-axis, what we think of usually as the y-axis, is numbered with imaginary units, so i's. And I'm going to give you several examples of how to graph these. So I'm going to use colored pencils and color code this. So I'll start with 4 plus 2i. So 4 plus 2i, the 4 tells me if I'm starting at the origin to go over to 4 on the real axis and then go up to 2i on the imaginary axis, and that's my point right there. So essentially it's a lot like doing the point 4, 2 with normal graphing. They just have the real and the imaginary part. It's two-dimensional, so that's why we have two axes. All right, let's do another one. I'm going to use orange. So negative 3 plus I. So negative 3 means go left 3 on your real axis. And then I just means I'm going to go up 1 imaginary unit. And so there is negative 3 plus I right there. I am not going to use yellow. I will use green next. So negative 2 minus 4i. You would go left 2 and down 4 imaginary units, so negative 2 and go down to negative 4. I'm going to make sure we get 1 in each quadrant and then 1 on each axis. So I'm going to use a dark blue next. So I'm going to do 3 minus 2i. So 3 minus 2i, we go over 3, down 2. So you go over 3 on the real axis and go down to negative 2 imaginary units. So that's how they look in the quadrants. Really, you could think of the first number as being x and the second part as being y and graph them like normal coordinates. The ones that usually trip people up the most are the ones that are on the axes. So I'll go through that briefly. If you just have one real number, like 2, I'm doing this in purple, you would just go to the real axis and it would be right on the real axis at 2. Let me get another color, I think I'll use pink. If we have just an imaginary part of your complex number, like negative 3i, then I wouldn't be on the real axis at all. I would just be on the imaginary axis at negative 3i. I put my little pink dot right there. And so that's what they look like when they're just on the axis. So graphing these is really not any harder than graphing points normally is in algebra. It's no big deal. So this took up maybe the top half of your page. I have narrow ruled paper, so it didn't take up that much for me. Let's draw a line just to separate that concept from the next one. So, you guys good on this part? Seems pretty straightforward. So down here we're going to talk about absolute value.
That's the thing with the 2 lines? And then
yes, so I want to start by reviewing just what it is with normal numbers. So if I normally have the absolute value of negative 2 and you have these bars, I usually try to draw them bigger and bolder so you know that they're not ones. We usually think of that as being on a number line, so I'll draw a number line really quick. And you would think of that as being the distance between negative 2 and 0. That's how we first defined absolute value when we were in middle school. And so the distance between 0 and negative 2 is just 2. If I did the same thing with a positive 3, I could put that over here, then that would be the distance between 3 and 0, and that distance is just 3 units, and it's 3. And then we sort of summarize that when you take the absolute value of a number, it made it positive. So that's absolute value of real numbers, is just how far it is from the origin on a number line. This is one-dimensional. When we start doing complex numbers, they are two-dimensional, and you do have the real and imaginary axis. And so we would be looking for the distance between the number and the origin. So I'm going to give you a definition down here. So I'm going to make a big absolute value bar. I'm going to put A plus BI inside that. And that basically means the distance between A plus BI, whatever that complex number is, and the origin. Okay, and so we'll talk about how we can do this with a graph, and then we're also going to use a formula. So I'm going to go ahead and put the formula there. I'll put another equal sign. Basically what we're going to do is we're going to use the Pythagorean theorem, and so the distance will be the square root.
Is that A plus BI?
Well, yes, A plus BI. And so we'll use the square root of A squared plus B squared, and I'll explain where that comes from. So this is a formula, but I'll explain why it works in a second. And you might want to put a nice box of some sort around this just to separate it from the examples. I'm going to do a couple of examples at the bottom. If you run out of room, you can always stick one of them on your practice page. So I'll scoot that up to the top. Okay, so if I have the absolute value of 6 minus 8i, I just want to do a quick sketch. I'm not going to do a full-on graph, but a quick sketch to think about where that is. So 6, I would go over to wherever 6 is. I'm just going to say this is 6. I'm going to say that negative 8i is right there. So this would be the point 6 minus 8i. What we're doing is trying to figure out what that distance is from the origin. Okay? So, to find that distance, you could think of it as using distance formula, which we've done before, or even simpler than that, it all goes back to the Pythagorean theorem. If we draw a little pretend line here, we can make a right triangle, and basically you have a side of 6 and a side of 8, and you could think of it as just being A squared plus B squared, and this would be C. So you could have, this distance is 6, so you'd have 6 squared, and then this distance would be 8. You could think of it as negative 8 since it goes down, but when I square it, it won't really matter if I call it 8 or negative 8, because it's just going to end up being positive. So you're going to get 36 and 64, and you get C squared. 36 and 64 make 100. I made this one nice, so the numbers came out easy. And then we square root that. So what's the square root of 100? 10. So 10 then is that distance. And so that's meaning that it's 10 units between the origin and this point 6 minus 8i. And once you understand that it's that, we don't have to draw a picture every time. We can just use...
So you just get rid of the I pretty much?
Yep.
Okay.
Because we're just thinking of it as units and units in a different direction. So let's do one where we just...
The I is just a placement.
The I is basically telling you it's on the imaginary axis. So it's like the difference between x's and y's. We have real and imaginary. All right, so we've got, let's do absolute value of negative 9 plus 3i. This one won't come out quite as nicely. And I'm just going to use the formula. So the distance, the formula is just the square root of a squared plus b squared. So we're going to take the I off of it and do the square root of negative 9 squared plus 3 squared. So you're just taking the number here and your coefficient here. We don't put the i's in there at all, which is nice. So negative 9 times negative 9 is still 81. And you could actually just put in 9 there if that bothers you, because it's going to come up positive anyway. And then 3 squared is 9. So 81 plus 9 gives me the square root of 90. 90 is not a perfect square, so what we're going to do with this is birthday. We're going to use the birthday cake method to do a simplification. So I'm going to take 90, and what prime number do you want to use for 90?
5. 2.
2 is easier. I'm not sure what it is.
45.
So that would be 45. And then we can divide by 5 really easily.
9.
Get 9.
3 and 3.
And then 3 and 3. You guys have that down at least. So we would have the square root of 3 times 3 times 5 times 2. So there's 3 squared right here, a pair of 3s. And so you'd end up with 3 radical 10.
Equals C.
Yeah, it just equals your answer.
Okay.
You can think of it as C as the hypotenuse if that helps you just relate this back to Pythagorean theorem. Yes.